All right, what's good, yo? I'm Link, and today we're gonna do more LeetCode. Let's do the uh, daily question of the day. Let's see. Okay, haven't done this one yet, so copy here for 0.5. Okay, let's see. Okay, so one thing that I'm gonna do different from the last time is I'm gonna try. I'm gonna time myself. I'm gonna do like 20 minutes, see where I can go, and then if I don't manage to finish 20 minutes, then I'll just get some hints, look at discussion, and try to go from there. I think the last time I spent like 40 minutes, 30 minutes trying to figure it out. I went the wrong path, so I think it's gonna be more optimal if I do it this way. Okay, let's see. Kth smallest in lexicographical order. More lexicographical order. Okay. Give me two integers the n and the k and the k. Return the kth lexicographically smallest integer in the range. Okay, so it's pretty much the same thing, but we want the kth smallest integer. Okay, so I mean, we already doing. Okay, so in this case, it's pretty much the same as the last one because the last one we had to return the list in lexicographical order. We had to build the list. This time we only need to return the kth element. So I think, let's see, I was wondering if it's possible to keep generating. We don't have to save it, right? So we keep generating until we find the kth. We accumulate the k as we go, and then we just return when we get to the point that we want. Um, oh, let's see. I guess the easiest way would be just generate the whole thing and return the element at a specific index, right? But we might, that's gonna give me a timeout for sure. But let's try this way first, and then we need to optimize, we'll do. Okay, so rest, try to do the same thing before me. Let me get this bigger. Uh, oops, didn't want to do that one. There we go. Okay. Gonna do we want okay so end gonna do DFS again. Def DFS. We need current and then let's see if I can remember. We need a current if length of current is greater or equal to length of n. Start length of n. Length of the string value of n. We also need an end, so we check if the lengths of it are the same, and we check. Let's do current equal to integer. In this case, nope. Actually, we do it string. We're gonna keep appending, accumulating the numbers. Let's see. If length of current is greater or equal to the length and length value of current it's smaller or equal to n, that means that we have a valid number. So let's that append current, and then we can return off this. If that's not the case, let's see, if that's not the case, uh, so, that means that if the we still have the problem that like, see, if the length is smaller, but the number is still valid. So if if the int value of the current greater, smaller, or equal to n, then we also want to append this. Okay, so we're gonna the int value, so this is gonna be int of current as well here as well. Int of current, okay. And then else, not else. Let's continue generating the rest of the numbers. So for I in range 0 to 10, we're gonna append from 0 to 9 elements. We're gonna DFS current plus the string of I. Okay, think that might be it. And then for I in range, same thing. So 0 to 10, we 1. We want no one element to start with 0. We're gonna do DFS string value of I. Okay, let's print this rest and see if we got the right elements. Let's return 0 this so we don't get an error. Let's see how that goes. Oops. Oh, oops. This is gonna be less. Oh, it's actually equal, actually. Bomb mistake here. It's equal and then it, yep. Oopsies. There you go. Oh, I gave submit. Oh, I didn't want to do submit. Whatever. This button's like so small. That should happen actually. If the length of the current element equal to the length of the string, that means that we have the same length. I'm gonna check if the integer value of current is less or equal to n. That's about right. We're gonna append this integer, we're gonna return so we know when it recurs on that one. If mm, I never print. I'm just this just for debugging. That's pretty great. Let's see what this gives me. Wait, why did I go to 140? Oh, I think it's that's return right here. It's an element. You're looking already, right? Wait, maybe that's it. Yep. Alright. Okay. Yep. Let's see if that makes sense. 1, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7. Okay. And then we just return res so we want the case. So if the second wait, who's the smallest? So if this schema is 1, yeah. Because if we want the second largest, the second smallest, then we just go 0, 1, not 2. Okay. See how that goes. Yep. So maybe a timeline problem. Let's see. Oh, it's gonna be yeah. Now let's improve this. So as we build the thing, we want to accumulate the current depth, probably. Yes. Uh, so we don't want to build this rest. Maybe, but um, let's see. The idea here is pretty much try to return early. Doodle, maybe, let's see. Um, Let me use this test case here. Oh, I forgot to time myself. At least I'm recording. Let's see how long. 11 minutes, that's fine. Let's see. I don't want to print all that, but uh, yeah, it's too long. Okay, let's see. Mm, Maybe. Wonder if this current app could work. Let's see. I could also like keep adding to the rest, and then once, you know what? Let's get rid of this. Let's try this. So once the size of rest is equal to k, yep, we stop pretty much. If length of rest is equal to k, we don't do anything. Um, and then we just return. So if 2 is 0, 1, we just return k minus 1. This might end the execution earlier, but we'll see. It's a little better, but I might still get a timeout here, but we'll see. Yeah. Let's see. Yeah, same thing. Hmm. Maybe we don't need to add elements in here. Oh, I think we do. Maybe we can do actually. As so we do head into this turn. Okay. Um, with the first one, we start 0, which is the smallest element. Problem here will be this for loop right here. That's not gonna work. Maybe DFS here might not work. Let's see, 14 minutes. Maybe DFS here won't work. Could use the single for loop with the mod solution, which might work. Wonder if we can still do with DFS. We should, right? Oh, maybe. Mm, that's fine. Because let's say we reach K after there's a pen right here, and then the next iteration, it would stop. Honestly, don't know why. How can I prove this? Maybe here. Okay, so maybe we don't need the elements. Hmm. I might switch to the mod solution, the one loop doing mod. That one's faster. And then maybe it's the adding to the array. What I can do is okay, count equal to 0. We don't do this for now. We don't need to append this. Actually, the append will actually be a count. This was one. Non-local a count. And then here the same thing. Down. And we rest is equal to 0. And rest right here. Blah, blah, blah. 1 of k count equals k plus equals current, right? Yeah. Is it current? Oh, but that won't work. No, 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 that won't work. I might switch to the. Okay, it's 18 minutes. I'll I'll try to switch to the iteration version of it. There's no way DFS won't work in here in this case, right? This don't work. It doesn't work. Okay, let's see. Hmm. Maybe maybe here. Eh, Right, because we don't have to do more computations. I don't think it's gonna change anything, but I said it was like don't run time. Nice, too small. Okay. Let's see. Okay, that'll go about 20 minutes. Let's see if we got any tips here. So we are arrange numbers in the tree. If we know the site, actually we can navigate a tree to find a digit. Hmm. So we arrange the numbers in the tree. If we know this, wait a sec. I'm not sure if there's a problem because we're getting a constant time right here, right? Oh, we know that the size of the number of nodes of every subtree. We can navigate tree to find the digits of the target number. Suppose n is equal to 4. It's easy to see that any subtree rooted at 1, 2, 3 has size of 11. And any subtree rooted at 5, 6, 7, 8, 9 has a size of 1, 1, 1, and it's okay. What about subtree at 4? The size of the tree at this level is n. The size of the running. What? N minus 3 times 1, 1, 1. Even any k, you can use a solution. We then use just n and k. Okay, let's see. It's if each each parent has at most 10 children. Hmm. You arrange numbers in a tree. If we know the size of the size number of nodes of every subtree, we can navigate the tree to find the digits of the target number. Suppose n is equal to 4 and then two numbers. It's easy to see that any subtree rooted at 1, 2, and 3 has a size of y, has a size of 11. Oh, is that right? Let's see if that's right. Okay, let's see. We have 4, 1. Huh. Hmm, I don't quite get this, honestly. Let me see the solutions right here. Find the case one. No, that's wrong. We can think of the problem as reversing tree. Each number can be seen as a prefix that leads to its children. We can effectively navigate the tree to find the case number without using numbers. For a prefix tree traversal, start with the smallest prefix 1 and traverse the tree. For each prefix, count how many numbers exist under it within the limit of n. Okay, count step. Use the hyperfunction count step to count how many numbers fall within the range of the current prefix. If the count is less than or equal to k, move to the next prefix. Otherwise, go deeper into the current prefix. Multiply by 10. Just in case. Okay, let me read this one again. Okay, this one I got it. Mm, okay, I see. If the count is less than or equal to k, move to the next prefix. Yep, Otherwise, go deeper into the current prefix. Multiply it by 10. Okay, that doesn't make sense. Okay, because we're going to add 1. So let's if we have 4, okay, multiply by 10 and 40, and then we can adding 41, 42. That makes sense. Just in case, as you move down tree or switch prefix, adjust k accordingly. This helps in determining how many more steps are needed to reach the kth number. Okay, just k. Okay, return result. Once k reaches 0, the current prefix is the kth number. Ooh, okay. Dark. Okay. Yk is greater than 0. Count is equal to self the count steps and current plus 1. Let's see. Hmm. Okay, so current is tracking the current number that we're at. Return current. Okay. Count. Okay, is less than or equal to k. Count less than or equal to k. Current plus equals 1. Count minus equals k minus equals k. Now current. Let's copy this whole thing. Let's see. While k is greater than 0, count is equal to self the count steps. Okay, so n is the actual n here. You change, you don't. Okay. Hmm. Okay, let's see. So current is the current number that we are at. K with minus 1 because we have the first element 0 indexed. Okay is greater than 0. Okay, we're gonna count how many nodes we have in the subtree of the next one, the next current. If the count is less than or equal to k, that means that we have oh, we're gonna change k as well. Okay. If the count is less than or equal to k, we increase current by 1. Let's say we have 2 as a 1 current. We count. If count is less than k, we go from 1 to 2 and decrease from k the number of nodes here. So for 1, we will get let's see count steps. Our current is less than or equal to n. Steps plus equals the min. N plus 1 and next. Okay, this is hard. The steps plus equals the minimum of n plus 1. I don't understand this part right here. Steps plus equal the minimum of n plus 1 next minus current. Oh, you're in here. I'm gonna have to walk through the code and see what does that mean. Okay. Let's do the example here. Let's just 13.2. Okay. So we start at 1 and k is equal to 1. Current, and then we have k. Well, k is greater than 0, okay? We count the steps. So we have, oh, n is the number. Okay, I thought I enforced the k. Okay, let's see. So we have current, which is 1, and then current plus 1, which is 2. We have 1 and 2. Count steps. Okay. Well, current is less than the limit. We add 1 step plus equals the minimum of n plus 1, which is 2, and 2, this is 2, minus current, which is 1. Current times equals 10, and excess equals 10. Oh, because we want, yeah, we want, hmm. Ooh, okay. Because we want 10, in this case, we'll be stop at 10. And then, hmm. Ooh, this is hard. We go from 1 to 10, and then when we go to 100, it's going to be too much. So we stop here. So we have 1, 2 elements, right? 1 and 10. Oh, we have 11. Oh, wait, well, 11 will be, uh, the first step of current should count for 1 and 10. And then for the 11, well, I don't understand why he did n plus 1, but okay. And let's take y for instance. Okay, I'm gonna pause here, walk through a couple examples, and see where I can go from there. All right, after like a couple minutes, I think I got it. So pretty much, let's see, let's walk through the code again. Oh, it's kind of hard. Okay, so we pretty much test, let's see, let's say the n is equal to 10. I want to keep this wrong, but it's okay. It's okay. Delete all this. Get rid of this. Okay, so we start with 1, and we want to get all the prefixes, all the range between 1 and 10. Let's see. Actually, no. No, we're gonna get all the range from 1 to just this case. And then let's see, we're gonna count the steps. So let's see. The number of steps between 1 and 2 pretty much is 2 minus 1. And then we can multiply both by 10 to follow the lexicographic order. And then we check the numbers between. Add to step. So this will be 20 minus 10. This is the number of elements in here. And then we multiply now by 100, 200. Or then the current now is greater than 10, which is what we set to be n. Then we're gonna stop and return all the prefixes. Let's say we have more prefix than the available k. So what's gonna happen is we're gonna multiply by 10. So between 1 and 2, we have too many prefixes. So we multiply by 10. and count step from 10 and 11, which is just one. Okay. So pretty much we count all the subtree from 1 and 2. If this is too large, uh, then it's the elements between the subrange. I'm gonna count the steps slowly until we reach the K. Okay, it is kind of hard. Let's see if we can code this. Mm, Let's see if we can code this thing. This video, by the way, helped a lot visualizing the thing. Okay, let's see. Uh, okay. That's how we're gonna start this. Mm, K is equal to K minus 1, so minus 1. Well, K is greater than 0. Once we reach 0, that means that we found our kth value. So we have current as well. Current is equal to 0. Actually, current is equal to 1. And then create a function here. So steps. Wait, what we need? We don't need to pass anything. It'll be all local. Okay. Let's see. I'm just gonna return 0 in this case. Come here. Uh, yeah. So yk is equal to 0. I'm gonna count steps. Occur steps is equal to steps. If 2 steps it's smaller or equal to A, that means that we have on that specific subtree, let's say from 1 to 2, we have enough nodes. So we want to increase current plus 1, and now current steps, current, and we also want to update K. Minus equals steps. Else, um, that means that we don't have enough elements. So let's say between 1 and 2, we don't have enough elements, right? We're gonna go slowly. So the lexicographical order is 1, 10. When we get to 10, we're gonna get all the numbers between, let's see. So we have 1. Let's say we don't have enough elements between 1 and 2. We're gonna go from 1, 10, from 10 to 11. If that's enough, we're gonna go to from 11 to 12 and then keep slowly increasing. That makes sense. So mm, the current times equals 10 and minus equals 1. So that means we don't have enough from 1 to 2. We're gonna go from 10 to 11, 11 to 12, 12 to 13. and then just decrease by 1. Okay, move this. Okay. And then yeah, we can just return correct. Good. Now we need to implement the steps here. Okay, so how I'm gonna calculate steps? We will always want to do between the current and the next element, so between 1 and 2. So the next will be equal to current plus 1. Uh, let's see. I do steps. Go to steps equal to 0. Let's see. That's why. Okay, so we do need a copy. Current equals current. We need a copy so we can update. Oops. This okay. Be more organized. While current less than or equal to end step current steps is the actually steps plus equals minimum because we don't want to go over end. So current and then end, but we will include end, so n plus 1. Actually, let's say we have 1 and 2. The current is 1, the next is 2. We want to count all the elements between 1 and 2, which is pretty much the minimum between the next, and n plus 1, and then this thing minus current, right? So let's say we have 1 and 2, and then let's say the maximum is 10. So we 2 is still good related to 10. So we want the minimum between 2 and 10, which is 2. And then the current is 1. So the numbers between 1 and 2 is just 2 minus 1, which is 1. Next time will be 10 and 20. Let's say this is in bounds. 10 and 20, the element between 10 and 20, 20 minus 10. Yep, okay. And then we just, because of lexicographical order, we always want to increase by 10. So current times equals 10, and also next time equals 10. So we always want to do between 1 and 10, no, between 1 and 2, and then 10 and 20, 100 and 200, because of lexicographical order. And then yeah, we just return. That's okay. Mm-hmm. It just looks good. Probably have some bugs somewhere, but let's try this, see what this returns. Oh, it did pass. Okay, submit. There you go. It was pretty hard. I ain't gonna lie. But yeah, let me know what you guys think about this one. This one was actually pretty hard. The, the coding wasn't that bad, but concept was pretty confusing. Okay, anyway, appreciate you guys for watching. See you next time.